In step 5.1, select if you want to use a fixed effect model or random effect model. The choice should be made based on the heterogeneity of your data. The Frequentist base model will be built and the summary should appear in step 5.2. If they do not show up, and you are sure that you have completed the previous steps correct, just refresh the app and it should appear. Now we will examine the model. Let's start with the original data table. Here, you will see columns for treat 1, treat 2, TE, SETE and SETE adjusted. First, an important note. The app automatically arranges treat 1 and treat 2 in alphabetical order. For example, drug A will always be placed before placebo because D comes before P. If the app rearranges your original data, it will automatically flip the positive or negative sign of the TE. For instance, if your original spreadsheet had placebo versus drug A with a TE of positive 1.8, the app will alphabetize it to drug A versus placebo and change the TE to negative 1.8. Do not worry about this. The mathematical meaning remains exactly the same, and the app handles this correction for you seamlessly. Now, what do TE, SETE and SETE adjusted actually mean? TE is the treatment effect, which is the estimated difference between the two treatments. In our example, a TE of minus 1.8 means the mean difference between drug A and placebo is minus 1.8 units. It tells you the direction and magnitude of the effect. SETE is the standard error of the treatment effect. It measures the precision or uncertainty of that estimate. A smaller SETE means the study is more precise, and the app will give it more weight in the final analysis. SETE adjusted is the adjusted standard error which the app automatically calculates for multi-arm studies to prevent double counting the shared placebo group. Before running the model, you choose between a common effect model and a random effects model. A common effect model assumes that all studies are estimating the exact same true effect, and any differences between them are purely due to random chance. A random effects model assumes that the true effect varies from study to study due to differences in populations, dosages, or settings. It accounts for both within study and between study variance. Because real-world studies are rarely identical, the random effects model is generally the safer, more conservative choice, especially if there is any noticeable heterogeneity. You might notice that the effect size in the results table is slightly different from your original data. For example, the original TE for Krekeler 2025 is minus 1.8000, but the model's mean difference, MD, is minus 1.8068. Why is this? Because the network meta-analysis model does not just look at one study in isolation. It pulls all direct and indirect evidence across the entire network. It calculates a weighted average, giving more weight to larger, more precise studies. Therefore, the effect size and 95% confidence interval shown in the model summary are the network-adjusted estimates, which are more robust than the raw, study-level numbers. Next, let's look at the heterogeneity statistics, which tell us how much the studies disagree with each other. I² is a percentage. It tells you what proportion of the total variation is due to real differences between studies, rather than random chance. An I² of 0% means no observed heterogeneity. Generally, an I² over 50% suggests substantial heterogeneity. Tau² is the estimated variance of the true effects across studies. It is an absolute measure of heterogeneity. On the other hand, tau is simply the square root of tau squared. It represents the standard deviation of the true effects across studies, expressed in the exact same units as your outcome. In our example, all three are 0, indicating perfect consistency across these specific studies. Finally, the app provides two specific tests for heterogeneity. The within-design heterogeneity measures the variation among studies that compare the exact same pair of treatments. For example, if you have 3 different studies all comparing druga versus placebo, This test checks how much those three specific studies disagree with each other. Between design heterogeneity is also called inconsistency. It is unique to network meta-analysis. It checks for disagreement between different types of comparisons in your network. For example, it tests whether the direct evidence comparing drug A to drug B matches the indirect evidence inferred by comparing both of them to a placebo. If the p-value for between designs is less than 0.05, it signals statistical inconsistency, meaning your direct and indirect evidence are conflicting, and you should investigate why. If the between design heterogeneity is not shown, it could be due to one of the following reasons. Reason 1 is that you only have 2 treatments in your network. In this case, you only need to look at the within design heterogeneity. Reason 2 is that you do not have closed loop in the network. Even if you have 3 or more treatments, inconsistency can only be calculated if there is a closed loop. If your network have treatments all compared to placebo but never to each other, there is no indirect evidence to compare against direct evidence. In this case, we cannot evaluate inconsistency because there is no overlapping evidence to test. Again, this is a feature of your data, not a mistake. The last reason may be that you have insufficient degrees of freedom. If you have a complex network but only one study for each comparison, the model do not have enough data points to separate within design heterogeneity from between design heterogeneity. In this case, the model will default to only estimating the overall heterogeneity. Now let's move to step 5.3, design specific within design heterogeneity. This table breaks down exactly which specific comparison is causing the heterogeneity in your network. In our outcome 2 example, look at the design column. You can see P versus A has a Q value of 19.597 with a p-value less than 0.0001. This tells us that the heterogeneity is coming specifically from studies comparing placebo versus treatment A. The other comparisons like A versus B and P versus B show Q values of 0 with no P values. This is because there's only one study or no variation for those specific comparisons, so heterogeneity cannot be calculated. This breakdown is crucial because it tells you exactly where to focus your investigation. Instead of wondering why your overall heterogeneity is high, you now know to specifically examine the studies comparing placebo to treatment A. Ask yourself, are these studies very different in terms of patient populations, dosages, study quality, or follow-up periods? This is where you should look for the source of disagreement. Now let's look at step 5.4, sensitivity analysis using the leave one out method. This analysis systematically removes one study at a time and recalculates the entire network to see how much each individual study influences the results. Click the button to perform the analysis. Do note that it may take quite long to generate this table if your network is big or complicated. In this table, each row represents one study, and each column represents a treatment comparison. The numbers show the influence or impact of removing that particular study. For example, look at Chung 2025. It has values of 0.3695 for A versus B, 0.1010 for A versus P, and 0.1846 for B versus P. These relatively high values, especially 0.3695, indicate that Chung 2025 has a substantial influence on the network, particularly for the comparison between treatments A and B. Similarly, Acharya 2025 shows high influence values across all comparisons, ranging from 0.2858 to 0.3816. This multi-arm study is clearly having a major impact on your network results. Higher values mean that when you remove that study, the network estimates change considerably. This could be because the study is very large, very precise, or has results that are quite different from the other studies. Here's what you should do with this information. First, cross-reference these influential studies with your risk of bias assessment from Step 11. If a highly influential study also has a high risk of bias, your network results may not be trustworthy. Second, examine the characteristics of influential studies. Are they very different from the others in terms of patient population, intervention dose, or study design? If so, this might explain why they're so influential. Third, consider running a sensitivity analysis where you exclude the highly influential studies and see if your overall conclusions change. If the results remain similar, your findings are robust. If they change dramatically, you need to be very cautious in your interpretation. Remember, finding influential studies is not necessarily a problem. It's actually helpful information. It tells you which studies are driving your results and where you should focus your quality assessment and discussion. In summary, Step 5.3 tells you which comparison has heterogeneity, and Step 5.4 tells you which specific studies are most influential. Together, they help you understand the strengths and weaknesses of your network and guide your interpretation of the results.